Hi, and welcome back to the Block 74 Apollo Guidance Computer series of videos that I'm putting together. Today is going to be part three, and we're going to actually get into some of the registers of the computer itself. In the last video, kind of gave an overview of how they're all laid out and kind of what the various functions are. But today we're going to get into one specific register. We're going to go into it in detail and understand it, and then translate that into a design that we can actually build using the 74LS series logic. Okay, so the first register we're going to start with is the Z register. And I'm Canadian, so I can say Z register. For those of you elsewhere, it might be the Z register, but this is the program counter within the Apollo Guidance Computer. And in the last video, we kind of talked about the way that the AGC, and this is kind of the central processor, and how the various components and registers are laid out, and the logic that provides kind of control for information coming into the register. So that's, they call this, in this case, the Z service, and the write to Z pulse. So this is how data gets into the Z register. And then we've also got logic, which is how data gets out of the register. Now, in order to um, enhance the capabilities of the computer and really maximize what they could get out of it, each register has its own little, I guess, quirks. So little features that the designers added to either simplify specific instructions or functionality within the computer. We're going to start off with the more simpler registers, and none of them are entirely simple. Everyone, like I said, has its own little quirks. But we're going to go with the ones that are a bit more simple to start off with, and then we're going to go to ones that are progressively more complex. So if you go into the documentation, this is how they've actually been built. You can actually see the schematics of the Apollo Guidance Computer. We talked about earlier that they're all implemented with these NOR gates in order to provide all the functionality. And you can see here, this is actually where two NOR gates are cross-connected to create a flip-flop. So this is kind of a storage element. Now, the Apollo Guidance Computer was designed with kind of a concept of almost bit slicing for all of its registers. So there's four modules which contain all of the registers for the computer itself. And the way that they do it is that they implement all of the bit, in this case, bit nines, for every single register. And you can see, here we've got an A register. So this is you can see the right signal here for the A register, and that's the actual storage element for the A register, bit 9. In this case, we've got the Z register. There's the storage element for the Z register, and Z register bit 9, and so on and so forth. So we're not going to implement it this way because it makes it hard for us to really break out each individual register, figure out how it works, and then design and troubleshoot it. What I'm going to be doing is instead of kind of this vertical slice of every single register's bit, I'm going to go more of a horizontal slice where I'm going to look at the Z register in its entirety, all 16 bits. And the kind of the bit depth of the Apollo Guidance Computer is each register is generally 16 bits. One of them is a parity bit, and one of them is a sign bit. So you've got basically 14 bits of data, and then, like I said, the parity bit for error correction, and then a sign bit. Now, this, if you kind of look at these as well, this is pretty complex, and can get kind of hard to decode. So instead, we're going to look at, like I said, this particular slice of the Z register. And thankfully, within the manual itself and the documentation, they very clearly define and describe what each register does and the functionality that it performs. And here is the Z register program counter. And this is actually some sections right out of the documentation itself that talks about kind of what the Z register does. You can see it's the program counter, and it stores the address of the instruction to be executed next. Now, when we looked at the registers and we talked about it, they're kind of two different kinds. Some that are directly accessible as memory, so they kind of replicate or look like that they can be accessed as memory, and they can also be accessed directly. So we can see here This is kind of what they call the L service, and it's broken into kind of the top part here, which is the write. So this is how data gets into the Z register. And then we have here the read. This is how data comes out of the Z register. Now, as I mentioned, some of these are what they call addressable registers, and the Z register is one of those addressable registers, which means you can kind of look up here on the diagram. It can be accessed either through kind of this mechanism here. So we've got kind of a write timer. This is the WT signal. And you notice that there's a little bar above it because all of the control signals within the Apollo guidance computer are negative logic. So that means if they're 1 means no signal, so no write timer or no write Z signal, and a 0 actually asserts. That means that if we have a 0 on the WZ signal, that means we're actually asserting that we need to write into the Z register. So that, as you're going through the design, kind of takes a little bit of to get your head wrapped around, because again, it is negative logic as opposed to positive logic. And we can see there's kind of 2 ways that we can write data into the Z register. One is directly. So this is, we have the write timer and then the Z register write enable signal. So when these 2 kind of come together, we will write data into the Z register. And we also have this addressable register service. So this means that, at least from the Apollo guidance computer, the Z register is also looked at as memory address octal 5. Now, because it's less than 8, octal 5 is the same as decimal 5. Now, it will only write it'll only sort of write into this if the addressable register write signal is asserted. So this is WSC control pulse. And then similar, it can be read out as a memory address if this RSC, or addressable register read control pulse, is asserted. So that's kind of the, again, how data gets in. So we can get in either this combination here or this combination. So this is the direct write, where we have a WZ control pulse. And this is if it's the XB5, which is the signal indicating that the memory address is 0005. And then, these through various logic is combined to produce this particular internal control signal, which is where do we enable to actually allow data to be written into that particular register. Now, because of the way that the Apollo guidance computer was built with kind of the flip-flops and discrete logic gates, it's often basically every write signal is kind of preceded with a clear signal. So basically, it'll clear the contents of the particular flip-flop combination before it writes the data in. Now, because of the components we're going to be using, and I'll get to that in a moment, we don't really need to worry about this kind of clear signal. We have kind of used some of the components to provide sort of reset capability. So if I need to clear everything in the computer, we're going to have a kind of reset, but we don't need to kind of assert this clear pulse each and every time we write into the register. Reading is a very similar or simple. Again, we have the kind of the read timer and the read RZ control pulse, and then we have the again the address 5, and then the RSC control signal, which allows us to read out. Now, if this were everything, and you can kind of see here, this is like where those read and write signals for the addressable register service are generated, and there's a wide variety of kind of what asserts these particular signals, but we'll get to that later. Now, as I mentioned earlier, every register has its own little gotchas, little special features that they've added in to make the computer more powerful. And in the case of the Z register, is during a divide instruction, so DVI, there are certain control pulses that can be asserted. One is Z15 and the other is Z16. And what this will do is that if these control pulses are asserted, we're going to write data either into the Z15 bit or the Z16 bit. Now, if you look here, it kind of looks, there's like, okay, well, if we're creating a divide instruction, or there's a test for sign, which is a BRI value, and then we'll look at the different timestamps, and it's like, well, okay, do we have to figure out all this logic for our particular register to implement? And the answer is thankfully no. A lot of this kind of logic here is implemented as part of the generation of various control pulses. So as we go through and look at in more detail the sub instructions and how they're executed, they actually will assert as part of that that sort of the execution of the divide instruction will make these branch checks and assert the appropriate control signal for the register to behave appropriately. So what we're actually just going to do is, for our purposes, we just need to make sure that when we see these control pulse, either the Z15 control pulse or Z16 control pulse, we will write the 1 bit into that register. Now, this is actually the one that I've built, and in the next video, I'll talk more specifically about how I've built this. But I've got a bill of materials of kind of how I've assembled it together. And we'll look at the schematic just in a moment to kind of show how all these pieces come together. I'm going to do a video that'll talk about sort of my logic and kind of philosophy of how I'm approaching the actual construction of the hardware and the different printed circuit boards that I've created in order to kind of simplify the assembly. But just as a high level, what I've done is I've created these kind of modular boards that allow me to populate all the various logic circuits and components. Got LEDs on the front so I can see what's in a particular register, some supporting components so that everything works. And then because each and every register and control card and clock is going to be different, I didn't design a custom printed circuit board for each and every card. If I did, this would very quickly become a very expensive project. So I created these more modular boards so that I can, again, populate all the components and then use basically wires to connect them all together. So it's a combination of a kind of prototype breadboard and a printed circuit board to kind of hold everything together. Okay, I'm just going to switch over to the kind of the circuit itself. And so this is in KiCad, and this is where I basically laid out all the various components. Now, the first thing is, if you're familiar with CAD, you may look at this and go, Kelly, they have buses in KiCad. You don't need to create all these bird nesting lines between all the different components. And I did try to use that in my first couple of iterations of designing the schematics. For some reason, my computer does not like buses in KiCad, and every time I tried using them, it would crash. I lost files several times. And so I said, okay, I'm just going to draw out each and every connection separately. So it does make things a little bit messier, but it works. Now I'm going to start with kind of the standard structure of most of the registers that we're going to be using. And if you followed along with Ben Eater's 8-bit series of videos, this is going to look very, very familiar to you. So each register is going to consist of, in this case, 4 74LS173 chips. Each of these contains 4 D registers. So because there's 16 bits, 16 divided by 4 is 4. So we need 4 of these in order to store all of the components. And then we have a octal transceiver, which is what we're going to use to write data out onto the bus. And because 16 divided by 8 is 2, we need 2 of them. And so you can see here we've got data coming in from the bus, so our various write lines, write line 1, 2, 3, and 4 here. The Apollo Guidance Computer numbers its write lines starting with 1. Most folks that are familiar with computers and design are familiar with things always starting with 0. But for the purpose of the AGC, they actually start with 1, so 1 through 16, as opposed to 0 through 15. And then we can see here writing data coming out onto the write bus. Now, like what Ben kind of described, is that we could have actually built this entirely using just the four 173s. But then, because we can use kind of the output enables here to push the data out onto the bus whenever we needed to. The challenge is then we can't actually see what's stored in the register at any particular point in time. So by using the register here to kind of bring data in and storing it in the register, and then using these bus transceivers to push data out, we can actually leave the output enables on all the time, so that we can use LEDs to show us the contents of the bus, and that's going to make it a lot easier for us to troubleshoot as we go forward. So a little bit of these of kind of how we've kind of wired it together. As I mentioned, we've got these output enables, which we've just tied to ground, so that these outputs are always enabled, so we can always see what's inside the register. We've got all our clocks tied together. So this is the clock connector, so that all of these will be clocked together. We've also tied together all the master resets for all of these registers. And that's what I talked about, that we won't necessarily be using the clear pulse, but we will be using kind of a master reset, so we can reset everything that's in the computer as well. And then we've got these kind of enables, which allow us to write data in. And this is where those control signals that we talked about, when do we determine when do we write data into this particular register. On the transceiver side, again, we've got the chip enable that we're going to tie to the read signal. So when do we read data out onto the bus? And then we have one other control, which is the A to B, which is what direction data is going to pass through this particular transceiver. So in this case, we just hard code it to 5 volts, so that we're always going to be going from the A side to the B side. And this you're going to see again and again and again as we go through each register. Now, where things are going to get a little bit different is on basically the control logic that determines when do we write. So this is kind of the write logic up here, and this is the read logic. So this is when do we take data from the bus to load into the register, and this is when do we take data from the register and push it out onto the bus. Now, a few things as I've just to make sure, we've got the fan in and fan out on the 7.4 LS series, which is about 10. I could have used some of the different kind of CMOS logic parts of the 7.4 family that have larger fan in and fan out, but I wanted to keep it fairly simple. Some of the CMOS versions have some more, let's say, quirks when it comes to making sure you have to ground or tie all unused pins to ground or 5 volts. The LS series gives you a little bit more you can kind of play around with them a little bit more and leave pins unconnected, and it's not as big an issue. So what I've done is I've added just a few buffers here and there. Probably don't need them, but the right timer is going to be a lot of there's going to be a lot of chips connected to the right timer. So I'm just going to buffer on each of my boards just to make sure we've got a good, nice clock signal for all the chips. And same for the reset, just to make sure that we've got a good, solid reset signal when we do need to reset. Okay, so we've got, again, the two scenarios of when we need to write data into the bus. So we've got the right timer, and we're going to use that as our clock to when we clock data into the register. And then we've got basically this combination of when we have a WZ signal asserted, or we have this direct addressable memory address 5 and the WSC signals asserted. So basically, through the logic, we've got, in this case, we're going to invert it. We're going to NOR these together, and then we're going to NOR those both together. So that we have our what's called the WSZ or WZG signal, which is tied to our enable. And that means that in any of these circumstances, either WZ is asserted, or we have the combination of XB5 and WSC, we will then enable our chip so that we can actually load whatever data we find on the bus. The kind of the flip side on the output. So in this case, because the transceivers for pushing data onto the bus don't have a clock output per se, we're actually taking the read timer and combining that into our logic as well. So we're going to invert it Same with the RZ. So this kind of, is the circuitry here is basically exactly the same as this. But then we NOR it again with the right timer so that we'll only push data onto the bus when the right timer is asserted. And because we've added this extra NOR gate, we need to invert it to get it back to the negative enable logic we need for chip enable. And because I had an extra NAND gate floating around, I just tied the two pins together so that we can save chips, because you can see here, and I'll show a little bit down, we ran out of, I used 6 inverters already, and there's 6 inverters on each chip. And rather than adding one additional chip just for the one inverter, I just thought I'd use some leftover gates in order to do that. So that, in essence, takes care of our loading data into the bus and loading data out in the bus. And I've created a little bit of a kind of simulator here so we can kind of see how it works. So just set all of these, because again, negative logic. So basically turn all of these off. And so right now, we've got our write line 1. I haven't simulated the entire 16 bits because it'll get pretty big. But if I see here, okay, I've got 1 bit, a 1 on write line 1. And this is my clock timer here. So I can click it and you'll see, well, I'm not loading any data into the register, no matter how many times I click it, because we haven't asserted any of these particular signals. Now, if I say, okay, we've got asserted a WZ signal, click the button, we load it in to this particular case, so we can actually load data into the Z register. And I'll just quickly clear that. This is my little reset button here. And then we have the other combination. If we have XB5 and WSC, and I click the clock, we load it in. So that's kind of our write circuitry up here. And then our read circuitry, again, is very similar. We just bring in the right timer. But I can say if nothing has been asserted, I can see that. And we've got basically a 1 on the RZG signal, which means we're not going to enable the writing out onto the bus. But if I check this to 0 and click the right timer, we can see we're going to get a 0, which means chip enable, because the chip enable on the transceivers is negative logic. So that means it'll write data onto the bus. Now, if that were everything, if the Z register were just a simple in and out bus, that would be it. But we have those two Z15 and Z16 signals. So going back to our schematic, here they are down here. And then we've had to add a little bit of additional logic down here to kind of support loading that data in. Now, we basically have these kind of like 2 scenarios where, when these signals are asserted, and this is something that took me a while to read back and forth and go through some of the detailed manuals of, when we get this Z15 or Z16 signal, do we clear the bus and just only write those bits into the 15 or 16? Or do we just take whatever is currently in the Z register and set bit 15 or 16? And in reading the documentation and kind of going through a couple versions, it looks like that the functionality is that you need to basically maintain all the current contents of the Z register, and then either, if the Z15 is a 0 and you get that signal, we set it to 1. Likewise for Z16. So we have this kind of scenario of, what do we load into bit 15 and 16 of our register? So this is our 4th 173, and that's basically responsible for bits 13, 14, 15, and 16. So again, we have 2 scenarios. So one, if it's normal, if there's no Z15 or Z16 signal, we want to just write in whatever data is on the bus normally. So WL13, 14, 15, and 16. And so basically what I've used is kind of this LS157 as a selector to say, okay, well, what do we load into these registers depending on what condition that we're in. So normally this kind of selection signal here is, we're going to generate it from a combination of basically a NAND of the two control signals. So if we don't have either asserted, we're just going to select the option A, and that'll just load the bus data in normally. Now, if we do have the Z15 or Z16 control signal asserted, what we want to do is then say, okay, well, we need to load the contents into the WL15 or the Z15 or Z16 bit. Now, because we're going to be reloading data into this register, we want to leave everything else. So what we've done is basically we've kind of made a little bit of logic here on this enable line to say, well, when do we actually load data in? And so we've kind of said that, well, if we're just loading it in normally because there is no Z or 15 or 16, we've got these, it's got an inverter and NOR gate that basically says, just load it in, and we'll load in these right off the right line bus. If it is asserted, though, we won't write in any of these. We won't basically touch them, but we do need to write either the 15 or the 16 into the D register. And so when we do this, there's a few things we have to worry about. One is we don't want to change bits 15 or sorry, bits 13 or 14. So in those scenarios where we're going to select kind of the B, or basically sort of instead of input 0, we're going to put input 1 on the selector. Well, we want to just rewrite 13 or 14 back in because we don't want to change it. And then we want to write 15 or 16 in. And we've added these OR gates here because we don't want to, if 15 is a 1 and we get another one, we don't want to change it. And likewise for the 16. So we only want to change the bit 15 or bit 16 if their respective control pulse is asserted. So I've added that to the simulator here so we can kind of see how that works. So right now we may have, if I got my Z01, neither of them asserted, again, because of the negative logic. So if I assert one, I hit the clock timer, we're going to load it in. And likewise for the Z register, or sorry, the Z16 register, we can load that in. So again, this is kind of, again, the little added complexity to that each register has its own little thing that we'll go through each one by one in order to replicate that functionality. So as I built it, the basic bill of materials in order to complete this register is I used 4 74LS173, and these are the D-type registers that we use to store the data. We've got the 2 74LS245 octal bus transceivers. This is the data. This is what we use to push data onto the bus. And then we have the 1 74LS157, which is our data selector that we use to handle that Z15, Z16 signal. And then just for the glue logic for everything to kind of work together, I used a 1 74LS04 hex inverter chip. So that's 6 inverters. We've got 1 74LS02 quad, which is 4 2-input NOR gates. We needed 2 74LS00 2-input NAND gates, 1 74LS32, which is 4 2-input OR gates, and then of course the 1 buffer, and then a bit of kind of glue, supporting components, 16 red LEDs that I use to, so I know what's in the buffer or at any particular time. I've got some bus resistors that I'm using. You can see here, and that's just for the resistors so that we control the current flowing through them. I've got a bunch of 0.1 microfarad ceramic capacitors. So each and every, you can kind of see them here and here. That's one of the nice things about building everything onto a standardized board is I can put these little filter capacitors really close to the power inputs on each and every chip so that they're be nice and happy as they operate. And then I've got the this kind of connector. So I'll talk about this more in one of the next videos around the actual design and kind of logic of how I've laid out the actual hardware. But I'm using this 96-pin connector in order to run most of the signals in and out of the computer. Okay, I think this one's probably gone long enough today. So next video, I'm going to talk about the B/C register, and then I'm going to do one that's going to talk about actually the hardware and how we build some of these components. Anyways, if you're interested in kind of following on, please click subscribe. And as always, open to feedback. Let me know what you want to hear more of or what you want to hear less of, and we'll see you next time. Thanks.